Okay, good afternoon, everyone. Thank you for attending today's webinar on Manual S. This webinar will be recorded and the recording will be sent out to all attendees. If there are any issues with audio, please write me in the chat. My name is Erica DeLello and I'm a project manager for NORESCO. And this series is sponsored by Colorado Energy Office with training materials created by Colorado Code Consulting. So Gil and I have been working with the Colorado Energy Office to provide trainings just like this one. Here we have a list of trainings that are offered in this series over the next couple months. If you are interested in registering for any of the other webinars, feel free to sign up through the link that's sent out in the follow-up email. We do also offer tailored group trainings or technical assistance for jurisdictions that are updating I-codes. So feel free to reach out to me if you are interested in any of those. And I believe in the post-training survey, there's also a question about if you're interested in group trainings. In addition to the trainings and technical assistance, we've put together a code adoption toolkit that reviews cost implications of changing code cycles, the benefits, and a lot of other compliance resources, including a troubleshooting guide that we've created that covers I-code conflicts, alignments, clarifications, and paths of compliance. Both of these resources can be accessed through the Colorado Energy Office's website. So throughout the webinar, we do want to encourage questions. Please use the Q&A function and I'll let a presenter know at the end of the presentation. The chat window can also be used to chat among participants, but please use the Q&A if you'd like to ask a question. There is also the ability to raise your hand at the end of the presentation and then I can unmute you and you can ask Gil directly if you have a question. And then as I mentioned before, there's a survey window that pops up following the webinar. Please take a minute to provide feedback so we can continue to improve on these webinars. Today's presenter is Gil Rossmiller. He's been in the construction industry for over 40 years. He was the chief building official for Parker, Colorado from 2003 to 2016. He served on the IRC and plumbing and mechanical code development committees for 2009 and 2012, and on the commercial energy code development committee for 2015 and 2018. And he's serving on the residential energy code development committee for ICC 2021 as well. Gil, are you also participating in the 2024 development now?
As a matter of fact, I am. I am on the Code Correlation Committee, my first time on that particular one. That will be a fascinating experience.
Well, hopefully we've got some exciting developments there too. Well, so I'll go ahead and stop sharing my screen here, Gil, and you can take the lead from here.
Okay, you should see Manual S review. Does that look right?
Yep.
Okay. All right. Sounds good. All righty. Okay. So we'll get started here. Just type questions in. If you got questions, no big deal. I'm going to kind of cruise through this bad boy. We've only got about 3 hours today. So we'll see if we can get that done within that amount of time. Don't panic. It's only an hour long. Gee, come on, guys. All right. She did a really good job. That's just as me. I'll have my email here at the end. If you've got any questions at all on this or any of this part of the series, do not hesitate to send me an email, ask a question, and I'll get back to you as quickly as I possibly can. Love to give you my 10 cents worth. So last week we went through the loads. So manual J, heat gain, heat loss, that's all it does. So now that we know that, this is the process by which the equipment is selected, okay? The one mantra that we'll leave with today is that there is no software that does manual S, okay? So repeat after me. There is no software that does manual S. It is up to the designer. There's plenty of things within the software where it tries to do the calculation and pick this equipment for you. But the process that we're going through today is up to the designer. The designer must do it, okay? So where are we at? Yeah, so, you know, this whole process, can't remember if I talked about this last week or not, but this is what we've done, is it not? With the energy code, right? Lowered U factors, raised R values, right? In order to quote, effective use and conservation over the useful, energy over the useful life of each building, right? The house is a system concept. So if, things rot, buildings rot from the inside out, who cares how well your HVAC system's been done, right? So here are the questions. How much energy does a window use? You don't need to answer, you just think to yourself. Okay? How much energy does any of the insulation use? Now, I'm not talking about the manufacturing process. I'm not talking about the life cycle stuff. I'm talking about sitting in your house right now. How much of that stuff? Like, what does it use? So if it's all about the effective use and conservation of energy, what are we talking about? Yeah. Clearly, the windows and the insulation doesn't use any energy whatsoever. You're not hooking electric wires or gas pipes to any of that stuff. It's the equipment, guys. It's our appliances. It's the size of the air conditioner. It's the size of the furnace to heat the house. That is what it's all about. And so all of this wonderful stuff that we'd be doing for decades, and we talked last week, yeah? How long has Manual J been in the code? Well, it's been in the I code since there was the very first one, the 2000 IRC. And it's been in codes before that, believe me. Okay? So what's it, a couple of decades among friends, right? So the key is that this whole process is where we actually save the energy. Everything else just lowers the size of our equipment, which in turn, right, saves energy. Enough talk about that. So anyway, that's what you got to keep in mind. That's what it's all about, okay? So here, turn on my little laser pointer. Here we kind of talked about all of this stuff that's up here last week. Yeah. So now what we're going to do is we're going to try to concentrate on this stuff down here this week. This is a shot from RightSoft software, and we'll probably get a few in here from Elite too to show what we're talking about. Okay. So if anybody's got questions about what we did last week, too bad we don't have time. No, ask questions, please ask questions, and we'll get to that. So what do we do? Well, first we'll talk about how big a furnace do we need? So that's our heat loss, yeah? So we've got, in this particular example, we had a little over 31,000 BTUs we needed to heat the house with. So I did Carrier, only because I had the specs. Doesn't mean that Carrier is any better than anybody else. So we have an input rating about 40,000 BTU. It's a 92.1 efficient, and we're not going to run off to the data there. I was just going to show you everything that we're going to be showing you from here will be screenshots from the actual product data itself. And during plan review, you should be receiving the product data in order to verify that what they've done is what the product says it'll do, right? Sometimes those can be relatively lengthy PDFs that might be 30, 40, 50 pages long. But we don't need that many. The designers can give you the sheets that you need that show you what you need to know, right? So we're going to take a look at this here. We just got a little bit of verbiage here. So we got what? It says I'm going to have an output rating of about a little over 33,000 for this particular unit. After we do a D-rate for altitude and efficiency. So here's the math, and we'll tell you how we got there from here. So the first one's easy. 40,000 times the 0.921 gives us this 36,840. and we're going to reduce it by 10%, and that's what gives us this total output at altitude for this. So now that, now you're asking, well, what the heck? What do you got? What is the adjustment for altitude for gas-fired appliance? Well, we've got manual S. There's a whole chapter on adapting for altitude. Okay, but we're going to look at the actual performance piece here for the appliance itself. In fact, I haven't found any gas-fired appliance manufacturer that doesn't tell you what the duration is for altitude. Every single one of them will. Okay. Then when we look at this, it's like, okay, per manual S, we can actually be 40% larger. So we would take, right, 140%. So we take our calculated load times 1.4. That means we could have an output capacity of about a little over 43,000 BTU. Ours is at 33, so we're in way good shape. Now, will there be times, especially when you guys are dealing with altitude, that it will be larger than that? And the answer is yes. Oversizing on the heating equipment is not as large an energy penalty as it relates to air conditioning. Air conditioning, it's a horrible oversizing thing, right? But there's reasons we'll go over when we get to air conditioning. It might be a little bit higher than the acceptable oversizing. So the reason for the whole going oversized on furnaces for heating side is that the blowers in residential appliances are pretty lackluster, okay? And they as in the designers, may need to go, so in this particular case, a 40,000 BTU furnace would actually work. I'll show you that it does. But because of the blower size, in order to get enough air to move, we will need to get a bigger blower. Well, I can't get a bigger blower than 40,000. I've got to go to the 60,000 BTU furnace to get a bigger blower. So if I ever see a plan that comes in and it says, hey, I'm going to be more like 180% oversized. But the reason I did that was because I needed a bigger blower to get my air conditioner to work. And as soon as I hear that, I say, oh, okay, let's move on with life. Okay, that is very unique to high altitude applications. Okay, we got that. So here's just a real quick section out of this particular manufacturer. And so this one is 40,000 BTU. This is just part of their model number. Something that's very important right here, temperature rise. Okay, very important that pieces meet the temperature rise because that's what makes the furnace work. Yeah, temperature rise, what's the difference between the return air temperature and the supply air temperature? And that's the temperature rise. In this particular case, if it's not between 15 and 45 degrees, it will not provide the BTUs of heat that you think it is. It's very important that this gets checked. And if it's not there, they need to adjust the fan speed. I'll show you how that works here in the next slide. The other things that we need to look here is this certified external static pressure. Heating was done at a 0.1, cooling was done at a 0.5, and that's what they did in the factory in their wonderful test lab. So at a 0.1 external static, it was moving 1,125 CFM, and at a 0.5 external static, it was moving 1,215 CFM. I'll show you where that works on the fan speed chart, because the only reason this is the quote certified is because that's the only two places they run the test. And when we look at the fan speed chart, you're going to see there's a whole lot more fan speeds than just one or just two. It's just fan math that they do the rest of the table on. This is the only time they run the two tests. This doesn't mean that my total external static pressure for ductwork and everything else can only be 0.1 for heating and 0.5 for cooling. That's not what that says. Okay, as long as the static shows up on the chart, you can use it. Here we're just talking about output ratings after duration and input ratings based on, upflow, horizontal. You can do it lots of different ways, right? Upflow, downflow, horizontal, depending on attic, crawl space, right? Basement. And so here you've got this little asterisk down here. And this is where it's telling me what's happening for input ratings. And so generally speaking, all gas appliances and manufacturers say, if it's 2,000 feet above sea level or less, we're good. Use this, we're in good shape. Then it says for everything above 2,000, in this particular case, it's 2% for each 1,000 feet above sea level. So in this case, I said, well, we're at about 5,000 feet. We're in Denver. So 5 times 2 is 10. So we had to reduce it another 10%. This is kind of unique. Most of gas-fired furnaces, you're going to find it's a 4% deration per 1,000. It's all up to the manufacturer. Just ask the manufacturer. I'm not going to question what the manufacturer tells me. They tell me it's 2%, it's 2%. They tell me it's 4%, it's 4%. So when you start getting up into 10,000 feet, you can see where this might be a big deal, right? And 4%, 10,000 feet, that's a 40% reduction in output capacity. Yeah, you do not want to put in a furnace that's undersized because we forgot to do the duration. The software has no clue how to derate for altitude. Does a lot of really cool things for altitude for heat gain and heat loss calculations, but it has no clue what the duration is for altitude. The designer themselves must do that all by themselves. And it's not hard math, you just got to do it. Let's see. Okay, temperature rise. So yeah, we can look at the right here, but I'm just showing you what the math is, what it does within the software. What we need to look at here is that we've already know what the output capacity is going to be because we've done our efficiency and we've done our duration for altitude. So I already know my output capacity. All the temperature rise is math, right? Relative to the output capacity, the output, and the CFM. That's it. And so the only thing that we can do to change this number here is what? In this particular case, this number is not going to change. The only number that's going to change is this airflow. And here's the teaser for next week. This is a big deal. At high altitude, things don't work like you think they should. Okay? So this is a very important point for next week. Be sure to tune in to find out what in the world I was talking about. All right. Just a really quick snapshot of temperature rise, right? You got the cool air coming down, sucks up nice, bottom return. Comes up through the heat exchanger, so you're putting a temperature probe up here, see what the temperature is, putting the temperature probe in here, and it's what the difference between the two is my quote, temperature rise. Again, temperature rise is correct, the furnace is working correctly. I don't care what the airspeed is. Kind of a clue for next week. Airflow is from our fan speed chart. Again, here I'm just going to point out what I was talking about earlier. So if I'm saying it was a 0.1 at and 125, so here's 0.1 static, and here's my furnace, and looks like it's shipped on medium low speed because that's the 1125. And 0.5 was doing 1215. So here's 0.5. Come down in here. It looks like air conditioning speed is set at high. Okay. The reason that this is important now, all of this stuff that we're looking at here, all of the manufacturer's performance data is all done at sea level. All done at sea level. Okay. we're going to talk about how air moves too. Okay, so we keep in mind that these are all sea level numbers, not 5,000 feet, 10,000 feet, down elevation numbers. So when we deal with boilers, so that's forced air furnaces. Hopefully I have that slide. I did a teaser last week, and oh, that's going to come up in air conditioning. We'll get it. So that was gas-fired furnaces. We'll talk about air speed here in a minute, I hope. Same thing with the boiler, 140% oversized. Okay. Then we get into these ski condo things. Okay. We've run into a lot of stuff where you've got ski condo businesses where everybody's out during the day skiing and everybody wants to come back and they take 8 showers all at the same time because they've got 14 bedrooms and several 3/4 baths and everybody's taking a shower at the same time. And of course they have to have what they call an indirectly fired water heater, and that's what this thing is over here. That's the water heater, and it just has a boiler loop, right? Coils inside there that heat the water. So they may end up needing a 60,000 BTU boiler to heat the house. But in order to provide, 200 gallons of hot water, or whatever it is they think they need, they might need 350,000 BTU boilers to do it. So the beauty of it is that the code gives us zero direction, does it not, on how big the water heater can or cannot be. Anybody can think of a code, you type it into your question, say, yeah, Gil, it's this section here that says the water heater can only be this big. Or the water heater needs to be at least this big. I don't think it exists, but you let me know. I can learn something today. The key is to those types of situations where we've got clearly way more boiler than we need to heat the building. It's very important that the controls modulate those such that only what they need to heat the house is running. Right? That's the key here. You don't want to tell them they can't do it. What you tell them is, hey, we need to control it so that we're only running 60,000 BTU on one of these modulating boilers to heat the house. You don't need to run all three, for crying out loud, to do that. Okay? Here, once we get into heat pumps, very quickly, heat pumps will have a balance point, meaning what's my outside design temperature and what's my heat pump capacity, and at what point do they cross? And I start to need help with heat. So air conditioning usually isn't the issue, it's the heat. And you end up oversizing your heat pump a little bit to get the heat up so that you can get it to work. Now in Colorado, I don't see too many heat pumps, especially air source type heat pumps, that aren't just already hooked to a gas-fired furnace. And so when the heat pump runs out of oomph, it just turns right over to the gas, right? Just switches over to the gas furnace, and that's what provides the heat. The key here is that we know what the capacity of the heat pump is. They give you some kind of a balance point diagram and tell me what the quote supplemental heat is. What are they doing? Electric heater in there? Is it just going to switch over to the gas-fired furnace or boiler to do the work? They just need to kind of let you know. So that was quick. And electric baseboard, pretty straightforward. If my room needs 1,000 BTUs, just as an example, and I got an electric baseboard that'll give me 200 BTUs per linear foot, I need a 4-foot baseboard. Yeah. So electric's pretty simple, especially if you use an electric baseboard, plug it in. It's just a little bit of math. And heating is the easy part. See, that was simple. Piece of cake, right? So, any questions on that? Type in. We'll go back over it and things like that. Now we're getting into cooling. This gets a little bit tougher. So, We're going to talk a lot about latent capacities and sensible capacities here. So let's just kind of have an overview of what that is. So sensible cooling is all about the heat. So imagine the heat from a light bulb as an example. That would be my sensible cooling. Then we get to latent cooling. So latent cooling is the moisture in the air and what we're trying to get rid of. Okay? So in Colorado, we don't have a calculated latent load. We talked about that last week. So what the heck is that? So what do you mean latent? How does that physically work? Well, let's imagine what's happening in our furnace. And so what we've got is we've got our condenser on the outside, our compressor, right? It's got the refrigerant in it. And what that is doing is that refrigerant's coming in and it's making the evaporator or the coil that's inside our appliance, inside our furnace, well, it's making it cold, right? And as the air the warm air goes through it, it cools it off. Well, the other thing that it's doing is that there's any vapor in the air, any water vapor, it's hitting that warm, moist air, is hitting that cold coil, and it's condensing. It's turning to water. Yes, that's the water you see coming out of your condensate drain. This is what we call a latent change of matter, meaning it changes from one state to another. In this case, it is now changing from what? Gas, vapor, to liquid. That takes real energy. And that's where this load comes from. Okay? So just imagine that latent cooling is the energy it takes to turn that vapor into water. And it's whatever's hitting the coil. Okay? And so as you can imagine, how much moisture-laden air is actually hitting a cold coil in your environment there in Colorado. It's very dry, right? We don't have a calculated latent load there. If you've got an air conditioner in your house and you go downstairs or you go down, where the AC is at, do you see water trickling out of your condensate pipe? Probably. So there's clearly some, right? So what we're trying to do here is we're trying to pick a piece of equipment that has what we call the sensible latent split. How much of my energy is taken up with just making the air cooler, and how much energy is taken up because I've got water in the air and it's turning vapor to liquid. That's what we're looking at, okay? That's a way to look at it, kind of picture that in your head. Or maybe it's like, geez, now I can't even get that out of my head, right? All right, so we're also going to talk about how air conditioning equipment is analyzed, yeah? So everything is going to have AHRI number. Heating and Refrigeration Institute Association, something like that. They're a standards writing organization, and they write a standard, which is good, that all equipment is tested with the same parameters. So that Trane can't say that their 2-ton air conditioner does more than a Carrier and more than anybody else. So what's good about this is that we have a very consistent test standard so that we know that we're comparing apples to apples. It's the same test standard. They go through the same pieces. Tell me what it does, okay? The bad part about this is that the test standard doesn't match what we're trying to design to. Remember what we were designed to last week? What was our indoor dry bulb temperature we were doing for air conditioning? 75 degrees, yes? Yes, that's exactly what it was. All the tests are done at 80 degrees. So when we look at the equipment's capacity, we do not want to look at what AHRI says my capacity is. This is why we will need the expanded performance data or more detailed performance data, not just what AHRI says. Like I say, AHRI is good, consistent standard. Everybody's got to test to the same thing. Problem is that, you know, we can't go by that because that's not what we're designing to. It also says that the outside dry bulb is what? 95. And what was ours? 90. So not only was the inside wrong, the outside is wrong. Can't use it. Good for testing, lousy for determining our equipment's capacity based on our design parameters. And do you think everybody's is 80 degrees and everybody's is 90 degrees, 95? Do you suppose it might get hotter someplace in like, oh, I don't know, Arizona? Nevada? Yeah, a lot hotter. Yeah, we've got these tables. We'll see. These tables go up to 115 degrees outside. And you suppose the capacity goes down? How is that outside thing working? Well, the refrigerant's going outside, and guess what it's trying to do? It's trying to get cooled off because it's carrying all the heat back outside. It's a heat rejection. Trying to get rid of the heat, it just absorbed, trying to make your house cool. Yeah? Yeah, well, it doesn't have the capacity of 115 degrees outside because guess what? It can't cool off as much, can it? You got 115 degree air moving through it rather than 90 or 95. Yeah. So that's why it's important to have those expanded performance tables. And it's important that the mechanical designer knows because the software has no clue. It only knows AHRI. That's what's in the databases and that's what the softwares have, and they're not correct. I mean, they're correct as far as AHRI is concerned, but they're not correct for what we're designing to. All right, here's what you've all been waiting for. This is how we determine when do we need two different systems for a house. Remember that from last week? Yeah, remember this table. This is the one that says, you know, we've got kind of the 8 cardinal directions here. And I was saying that, hey, if it's a production builder, we're going to pick the one with the highest load. Notice, right, we got no calculated latent load. And we picked the ones with the highest sensible load. Okay. So let's see. So here's the highest, 15,832. So which is the lowest? Here. 12,963, so call it 13,000. So 13,000 to 15,800 is what? 2,800 BTU. So the difference between the highest load and the lowest load isn't even 3,000 BTU. Air conditioning units only come in half-ton increments. That's 6,000 BTU. Did I tell you what a ton was? Well, if I did, I'll tell you again. Why is it a ton? Well, because it takes 12,000 BTU to melt a ton of ice in an hour. There you go. So 12,000 BTU for a ton of air conditioning. And so many of them come in half-ton increments. And some of the higher efficiency ones, the fancier ones, they only come in 1-ton increments. And so if we're less than half a ton, we're not going to get a different system. It's going to be the same one. So we will be installing the same air conditioner regardless of which way this place faces, because there isn't a big enough difference to worry about. You know, we get into 7,000 or 8,000 BTU difference, we might have a conversation with the designer to say, hey, did you want to think about doing a different unit? Or, well, we're using pretty good equipment. That's a 1-ton difference. So, right? Depends on what they're doing for the manufacturer. So there's the T's from last week, and you're going to have to wait for airflow for next week, and why it's important about temperature rise and stuff. Okay, so that's the answer there. Cool, huh? Cool stuff. Here, same thing. This is just one out of Elite. Same thing. So you're just looking to see, this one's at 17,640. Looks like here's right, 15,262. So again, what? Not even 2,000, maybe a little over. Not worth, yeah. So No matter which way this bad boy is facing, it's going to be the same air conditioner, be the same size. So we don't have to worry about it. All right. So now that we've kind of gone over that a little bit, let's pick an air conditioner. And this is good for you designers. Hopefully we got a bunch of designers on here. This is exactly what you're supposed to do. All right. All right, so here we got, what we're trying to do is try to get a piece of equipment that's as close to our sensible heat ratio, okay, our J sensible heat ratio, and that is sensible load divided by the total load. And that's how we get our sensible heat ratio. Well, our total load and our sensible load are identical because we have no latent load. Yeah. So if we do the math there, it is 1 every single time. We're not going to find a piece of equipment that's a 1. We're going to get as close as we possibly can because guess what? Didn't we just have that conversation? It's like, do you actually see condensate coming out of the condensate drain in your basement? And you'll go, yeah. It's not running like a faucet, but it's not like there isn't 0. Okay? So there's the difference between calculations and real life. How do you like that? All right, so let's see how we do this. So here's just a very small screenshot of something that there are many, many pages of in detailed cooling capacities. Okay? This chart will go all the way up to 115 degrees in 10-degree increments. So it's got 105 and then 115 to do that. So let's see. So we got, right? So we're going to use 63 degrees. So, right, 75 degrees. We were talking about that last week. At 50% relative humidity is that 62-degree wet bulb. Remember the sling psychrometer. Yes, wet bulb and dry bulb. So we're going to use 63. We'll look at this footnote and explain what that means here in a second. So we're looking at that, and we're going to start with this 800 CFM piece. Okay. Then we're going to, so we're looking at, right, that 15832, that's what we're looking for. We got 0 latent, so let's move on and keep looking at this, and we're going to show you some pretty cool stuff with this chart. So the air entering the condenser, outdoor units, the outside dry bulb. That's what this is, right here. 75, 85, 95. So Denver, we were actually at 90. You can be within 5 degrees. So going up to the 95 is okay. You could use the 85, but nobody's going to do that because it's showing a higher capacity than at 95 because remember the condenser on the outside is trying to cool the refrigerant, and the hotter it is, the less capacity it has. So going to 95 is perfectly acceptable. You can actually interpolate between the two if you want, but there's really no need to. This will work perfectly fine. Then if we do some math. So what it's telling us here is that we're using this 63-degree wet bulb. We're coming across here to sit 95 degrees on the outside, and it says I have a total capacity of 21,600. And I have a sensible capacity of 16,080. So if I do the math down here, it'll tell me what I got left over. So right now, that's my sensible heat ratio. Total divided by sensible, 0.74. And so let's see what that little footnote said. I think that's what we got next. Yeah. So the footnote at the bottom of these, 50 pages of stuff, it tells me that this little double cross means that I'm doing it at 75 degrees indoor. Everything else is done at, guess what? We just talked about that. Yeah. That's an AHRI number, which is good, but this is what we want. They've started doing that in the last few years, which is awesome because before you had to do a bunch of math and it was like hard to do and let alone try to explain, right? So now we have our own little row that we can deal with, all right? So we have a whole bunch of excess latent capacity, do we not? So let's take a look at something. Remember how I said airspeed affects capacity, and airspeed will affect stuff? Well, we can see that right here in this chart. We're going to look at this up here. Look, 63 degrees, and we're going to bring this over. And look, the total capacity has gone down slightly. And guess what? So has the sensible capacity. Why is that? Why do you think that just going from 800 to 700 CFM with the same parameters, it's done that? What the heck? What's happening to the coil? If I'm moving less air across the coil, is the coil getting warmer or is it getting colder? It's getting colder, isn't it? Yes. And so now it's going to have more latent capacity because the coil is colder. So when I'm in a humid environment, I want to try to run this as slow as I'm allowed so I can really have some good latent capacity because I got humid air. I need to dehumidify. In a warmer climate, I'd rather use a higher fan speed or a drier climate because I have more, it's all sensible. I have little to no latent capacity to worry about. And we can go on and on. The charts will show the same thing. The higher fan speed you go, the same thing happens. Cool, cool stuff. So clearly we've got lots of excess latent capacity. So we can actually, right, do some math and get this down to a point, get it to a 0.87. Right, so we take it and we got 5,500 BTUs and we need 0, right? Divide it in half so we can get down to that 2760, no problem. We can just add it right back to sensible, can we not? Why wouldn't we be able to? I don't know why. Yeah. So the total capacity doesn't disappear. It's still giving me 21,600 BTU a oomph of air conditioning capacity. It's just deciding what's the sensible latent split. How much water is actually condensing on that coil? In our environment, next to none, relative to where I'm at in Minnesota, right? We're down there in Florida. Yeah, it's a lot different. Not only got altitude dealing with us, we got, dry air. Yeah. So using these numbers, we're going to be just fine. Okay? Just fine. Yeah, now we can be up to 15% oversized here. So here, we're actually a little bit oversized, are we not? A couple of thousand BTU, maybe 3. But the key here is that you're allowed to use the smallest available coil. Okay, smallest available piece of equipment. So if I went down the next size, which I can't, but this is the smallest one they make, it would be too small. Okay, and the fact that we're within a half a ton, we can move on with life. Okay, because we're not going to change anything. Okay, yeah. You're always allowed to, even if it's more than, even if it gets up to 30% here, if it's the smallest unit that company makes, that's what you get to use. Yeah, that's what you get to use. Let's see. So yeah, 0.87, it's close enough. We're in good shape. What about the effects of altitude? How does that affect? About affect the airflow. So if I'm moving 1,000 CFM of air, am I still moving 1,000 CFM at 5,000 feet? And I know half of you are saying no. Half of you are saying, I don't know. Yeah, you're moving the same amount. Yeah, you're still moving 1,000 CFM. It's just that the air here is a lot less dense, is it not? It does not have the capacity to carry heat and cooling as it does, especially cooling, as it does at sea level. Yeah. So we need to move more air at altitude to get the same capacity for performance, or we need to derate the capacity. Now, Manual S does both. Most of the designers I'm familiar with in Colorado and dry climates prefer to increase the airspeed. And why do you think that is, guys? Because we have a really low latent capacity and more sensible. Moving more air makes the coil warmer. Yeah, satisfies the air conditioning needs. Yeah. Yeah, everything is performance is at sea level. Talked about that. We've got to make adjustments for altitude. Air conditioners, I've yet to find anybody that has what you do for altitude and air conditioners. I don't know of any manufacturer that's telling us what to do, but Manual S does there in Appendix 6 and has. There's the original Manual S, it's got increase in airspeed, and the new Manual S talks about derating the equipment. So here what we have, if we're increasing the airspeed, is what we call an air density correction factor. Okay? So what we would do is we take that 800 CFM, that's what we started with, yeah? That's what we started with there in that sea level chart. We're going to divide that by our 0.832, and that gives us about 962 CFM or thereabouts. Okay? Remember, this is just all math at this point, and once we get up to real life, that's a whole nother deal, is it not? Yeah, so the idea here is, do we have, can we do it? And you keep thinking, well, Gil, how did you know to pick 0.7 static? How did you know what you were going to do there? Why didn't you use 1 or 0.8? A question that will be answered next week. Yes, that will be next week. All right, so we're looking at our fan flow here. Really, can we get it? Well, yeah, we can get this 995 in here. No big deal. Sure, we can do it. Designers will not want to do that. Designers are going to say, you know what? I'm not going to design anything. I need to be able to go up a speed, especially at altitude. I'd rather try to get my paperwork and everything down at the medium high and not try to push the envelope there. Hence the need, right? Right now we've maxed out, haven't we? Yeah. Well, maybe if I can get the ductwork to work at a lower static, external static, which we'll talk about next week. But I sincerely doubt it. You're not going to get it to work. Not a lower external static. Let's see. Yeah, so what we're doing here, 0.9. Oh, well, I don't know why this is still in here. Why do I have, didn't we just look at this slide? Cooling. Oh, this is weird. Oh, geez. Oh, man, we don't want to get to this thing that fast. Oh, my goodness sakes. Surely we have questions to go through. Boy, did I fly through that bad boy. What do we got? We got something, Erica, we can talk about? Certainly that we do.
Yeah, we do. We've got a few questions for you here, Gil.
Good.
First off, how does calculating the new SHR, adding back half the latent capacity, affect your decision for equipment selection? For example, can we just use the original SHR calculation in the selection process?
Well, you can. So when we're looking at this, you need to start to decide. So what you have to do, the idea is that we need to satisfy both. So when we look at our calculation here, let's see if I can get back to the slide. Oh, that's what I want. We need to satisfy this right here. We're always going to satisfy the latent piece of it, piece of cake. Okay? This is the one that we need to satisfy. That's sensible. there are times where unless you add half of that latent capacity back to the sensible capacity, you might think you have to go up another half a ton. Okay. And if you go up a half a ton, that might be too big. It might not work well. So that's, we talked about that, to begin with. Would it be horribly oversized? No, but it would be oversized to the point where it might not perform like you think. That's true. It might still short cycle on you. Okay. So I think it's worth the exercise because it's not difficult to do, right? Once you as a designer, once you know what the actual capacity is at sea level based on your CFM that you want to move, doing that math is not difficult, okay? To find out what this number really is. And that's truly the split right there. And you can adjust that certainly within the right soft. I'm not familiar with Elite, but you can adjust that in the right soft. There's a field that you can do it and then it shows up on your report, okay? That's the key. You need to be able to match what the load is, okay? And ours, was what, 15, right? Ours was 15. Well, if we go back, it was pretty close, right? You might have said, that's just too close. If I were just to look at the performance chart, that 800 CFM, it's not giving me that, almost 16,000 BTUs of sensible. But when I realized that, hey, I'm increasing the span speed not only for altitude, right? But I got all kinds of excess latent, and it's not like, right? It's not like the 21.6 disappears. It still has that total capacity of 21,600. It's just, what is it doing? Is it doing sensible or is it doing latent? Well, I'm telling you, we don't have latent capacities that are latent loads that are probably even near 1,000, even in reality. Okay? And so that's why I think it's important to do that. Just to do the math, because you might be oversizing it and you just don't even know it. Cool.
We've got another question for you. If the smallest manufacturer's equipment is still oversized, does that indicate that the cooling strategy needs to be reevaluated using a different type of equipment?
Well, that's an excellent question. The code doesn't require you to do that, okay? So for instance, if Carrier, the smallest unit they had in this particular example was way too big, twice the size it need to be just for fun, just make it really bad. The code doesn't require you to do anything else or go back and use another piece of equipment. It does not, okay? That would be up to the designer. I think that's what they should do. You see that a lot with two-system houses. So I suspect a lot of you see two-story houses with a full basement that has a furnace in the basement that does the first floor and the basement area. And you have a furnace on the second floor sitting in a closet that does just the second floor. And I suspect they have a heck of a time trying to find a small enough unit to do that second floor than if you just have a single system. And so there's plenty of times when the calculated load for those second floor areas might not even be a ton of air conditioning, not even a ton. And many times, the smallest unit many of them manufacturers have is 1.5 tons. Okay? So the code says it's okay. It doesn't say you have to change. Okay? Right or wrong, good or bad. That's what it says.
Do you happen to know what the code section is that says that? Got an attendee.
As a matter of fact, I happen to know almost where that exactly is. Let's see. So we're going to get into the residential code. Yes. We're going to go into mechanical heating. I think it's going to be in here. Cooling. General is going to be in general. Equipment sizing. All right. So theoretically, you can see the code on my screen. Let's see. Yeah, so here it is. So the specified equipment or plane manufacturer published capacities cannot satisfy both total and sensible heat gains calculated in accordance with the approved heating and cooling calculation method, manual S. The next larger standard size unit is specified. Okay. Then it talks about variable flow pieces, but we need to be within the large range. So if it's a modulating furnace, for instance, I'm going with the highest capacity, not, well, it'll probably never reach second stage, but first stage it makes fine. No, you do it to the highest. You do it to the highest. Yeah, it says, yeah, heating and cooling equipment shall not be limited in the capacities determined that manual S where either following conditions apply. So the idea is that, and it doesn't say it exceptionally clearly, but the intent is that if it's the smallest thing they got, you're done, right? And if you need to go up a size to get it to work, go up a size. Yeah, and it didn't used to say that. 15 was the first time that came in. And that was a big deal. I think the other piece that got really icky in the beginning is trying to get this coordinated with Energy Star requirements. That's kind of been ironed out because the total load a lot of times, right, is a lot larger. If you looked at the total load, right, total load's only 15. And this one's 21.6. It's about a half a ton difference, isn't it? Yeah. Yeah. So this is what we want. This is what I concentrate on right here. And just make certain that folks have actually done the math here. And that a next smaller unit wouldn't work. Okay. Yeah, many times, most designers don't monkey with this. They don't know enough to do it. That they'll just pop in what the manufacturers, the AHRI data is, and they don't manipulate it, which is why it's important to get the expanded performance data so that you can actually see what it really does. And hopefully they got enough wherewithal to actually change the numbers within the software, so you don't have to, right? You don't have to do the math for yourself. Good questions. Those were good.
Great, thanks, Gil. I think that's all the questions that we have for today. We've got a couple minutes remaining, so Gil and I will stay on the line for just a little bit longer. If anyone wants to raise their hand or submit any more questions, we'll be here. But otherwise, thanks again, Gil, and thank you everyone for.
You bet, no problemo.
All right, Gil, I'm going to go ahead and end the webinar now.
Okay, sounds good.